Good morning, everyone. So today, what we want to do is first go back to the concept of orbital energy and orbital speed and relate both to each other and discover interesting facts about orbital motion. And then we'll try to see if we can, and we'll be able to do it, by the way, relate the orbital position to the time. Because so far through the orbit equation, we had been able to relate the orbital position or the orbital distance r to the true anomaly, but that didn't give us the explicit relationship between true anomaly and time. So we're going to do that through Kepler's time equation today. But at first, we're going to look at it from the circular orbit perspective. And then in a follow-up lecture, we will extend that concept to elliptical orbit, which is quite a bit more evolving to do it. And we'll have to make use of a new variable for elliptical orbit called the eccentric anomaly. But today we're going to restrict ourselves to the circular orbit case just to begin with, okay? But first, let's go back again to the concept of orbital energy and velocity or speed. Okay, so first, let's focus on orbital energy a little bit more. We'll discover some very interesting facts. So if you remember from before, we had the orbital energy was equal to speed squared over 2, that is your specific kinetic energy on orbit, minus mu over r, which is the specific gravitational energy for a spacecraft orbiting a primary body. Now, one thing to realize is that, as we mentioned previously, this orbital energy is constant for a Keplerian orbit or for the two-body problem, okay? What it means is that this particular equation has to hold at any point along the orbit. So, for example, if you look at the orbital energy, specifically at the perigee, then we could say that this also has to be equal to speed squared, specifically at the perigee, over 2, minus mu over the perigee distance, which we had denoted previously with RP. Okay? So again, the reason why I'm able to say this is because this was shown to be a constant. So that was one of our fundamental integrals. And thereby, I can evaluate it at any point along the orbit and yet always get the same number for the orbital energy. So here I've just selected arbitrarily the perigee as a point of interest, and that's why I can write this down here. Okay? Now, furthermore, if you go back to the concept of specific orbital angular momentum h, which is just the norm of h vector, which happens to be then the norm of position vector cross product with velocity vector, like that. While this is also a constant of the two-body problem, and therefore, if I want to evaluate it, set the perigee, same point as here, then what I can write is that this is RP vector cross product with VP vector, like that. And this is quite interesting because at this particular point at the perigee, if I were to draw a quick orbit here, with M1, the planet, and the perigee being here, well, at that specific point, you have the perigee position vector, RP, but the velocity vector at that particular point, because the velocity is always tangent to the orbital path, would have VP here, and there it means that those two vectors are perfectly perpendicular to each other at that specific point. Okay, so as a heads up, there are only 2 points along an orbit where those two vectors are perfectly perpendicular, at the perigee, but also at the apogee on the other side. Okay, where we would get RA vector and VA vector also being perpendicular to each other. At any other point along an elliptical orbit, those two vectors are not perpendicular to each other. Now, along a circular orbit, they are always perpendicular to each other. But along an elliptical orbit, only those 2 points have that special property. So going back here, it means that I can now rewrite that using the fact that the angle between those two vectors at the perigee is pi over 2 radian. To just say, well, I'm going to take the magnitude of the first one times the magnitude of the second one times sine of the angle between those two vectors at the perigee. So sine of pi over 2 is 1. So all I get for the specific orbital angular momentum h at the perigee is just rp times vp. Okay? Which means that going back to my first expression for the orbital energy at the perigee, I can then rewrite it differently by making use of the fact that Vp square, which is what we have here on the numerator, the first term, will be equal to h square over rp square. Okay? So I'm just going to substitute this into that first expression, right? H square over rp square over 2 minus mu over rp. Great. And turns out that this expression for the orbital energy evaluated at the perigee can also be rewritten as minus mu over 2a. So how to go from here to here? I'm leaving this up to you guys to figure this out on your own, because this is one of the problem questions, okay? Up to you, right? I cannot do everything for yourself. You sometimes have to work a little bit. Happy face. All right. So now that gives us a second expression to evaluate the orbital energy of any orbit, essentially. So to summarize, now we know that orbital energy is v squared over 2 minus mu over r, but also equal to minus mu over 2 times a, where a is the semi-major axis of the orbit. So this last expression is very useful because it shows us that the orbital energy is in fact related also to the size of the orbit, okay? Through the semi-major axis, which quantifies the size of our orbit. The bigger the orbit, the larger the semi-major axis is, okay? So what it means is that if you have an elliptical orbit, then in that case, we have our semi-major axis A, which is a positive number, okay? 10,000 kilometers, for example. And that means that the orbital energy for an elliptical orbit with a positive semi-major axis ends up being negative or less than 0. Okay? Now, if you look at a parabolic orbit, I'm going to put orbit in quotation marks like that because, as you know by now, parabolic trajectory is not an orbit because it is open-ended. It's not a bounded closed orbit, right? Remember the conic section discussion we had? So parabolic orbit or trajectory happens to have its semi-major axis to be equal to infinity. Just from a geometrical point of view, because it is an open-ended trajectory, it doesn't come back on its own. we say that the semi-major axis is in fact equal to infinity. And that means that if you plug A equal infinity in that expression for the orbital energy we just derived, we end up with an orbital energy exactly equal to 0, like that. And the third case we're going to look at is a hyperbolic orbit. And again, orbit in quotation mark, because it's not truly an orbit, but rather a trajectory. In that case, we have our semi-major axis, which now becomes negative. Okay, again, this is just a geometrical property of a hyperbola. That quantity is a negative number. Plug this back into our new expression for the orbital energy, and you'll get that the orbital energy is now positive. This is very neat, because this tells us that if the spacecraft has a negative energy or has a low amount of energy, it will not be able to escape the gravitational field of the primary body attracting it towards itself. Okay? And therefore, our spacecraft will remain on orbit forever about M1. Now, if the orbital energy increases up to a specific point where we get to orbital energy equal to 0, it means that now we just have barely enough energy to escape the primary body or the planet. We would escape its gravitational field and end up eventually at r equal infinity, very far away from the planet, with a speed equal to 0. So we barely have enough to escape, and then we come ultimately with no energy left, or in other words, with a velocity or speed equal to 0. Of course, this is a theoretical concept, because in space, there's not only one planet attracting a spacecraft, but multiple planets. So if you do indeed escape one planet, what's going to happen ultimately at r equal infinity is that another planet will pick up the gravitational attraction on that spacecraft and then accelerate it towards itself. But assuming that all we have is a planet and a spacecraft, then we say that in this specific case of a parabolic orbit, we end up very far away with no residual speed left. But if you keep increasing the energy and end up with energy being a positive number now, it means that you have quite a bit more energy than the two previous cases, and thereby you are able to escape the gravitational pull from the planet. Not only that, but end up at an infinite distance from the planet with a positive velocity or positive speed. Okay? Okay? And you keep traveling with a positive speed at infinity. So elliptical orbit, not enough energy to escape the gravitational field. Parabolic orbit, barely enough to escape, yet you end up with no residual speed at infinity. And hyperbolic means that you have quite a bit of energy and essentially enough to escape the gravitational attraction and end up at infinity with some residual speed to keep moving forward. Okay? So all of this had been derived, those conclusions or implications have been derived from the new expression of our orbital energy we have just derived here. Okay? Good. So that's it for additional concepts about the orbital energy I want to talk about. Now let's move on to the orbital speed or velocity. And I think the proper naming of that subsection should be speed and not velocity, because again, we're talking about the magnitude of the velocity vector in that subsection as opposed to the vector form of it, okay? So although if you look at the lecture notes, it's written velocity, I'm going to say speed instead. Okay, well, let's go back to our first expression for the orbital energy we had, and that was this equals specific kinetic energy, and then the gravitational energy contribution there. Well, what we can do with this is solve that expression for the orbital speed, which will become orbital speed equal to orbital energy plus mu over r, 2 times this, and then square root of all that. Okay? I've just solved the orbital energy equation for the speed, essentially. Nothing too difficult here. Which, using our new version of the orbital energy equation, which is minus mu over 2a, I can rewrite that expression as being equal to square root of mu times 2 over r minus 1 over a. So speed equal to this. Wow, that's a very neat little equation, because that equation, and this is speed, boom, allows you to calculate the speed at any point along the orbit if you know the orbit dimension quantified through its semi-major axis at any point or at any distance from the primary body or the planet. Okay? So again, it means that if you have an orbit like this, M1 planet, and say you'd like to determine the speed at that point. Fine. Well, you know the orbit size through its semi-major axis, which is again from the center to either side of the orbit. That's your semi-major axis. Not from the planet, which is here at one of the two foci, but at the origin. Okay, let's call it 0. So that's the size of the orbit through A. Now all you have to determine is at what distance from M1 would you like to calculate the speed. Is it here? Is it at the closest point, at the perigee? Is it over there? Just plug in the distance you are interested into calculating the speed at, and then boom, plug and play, you get the orbital speed. So this is the equation equivalent to the orbit equation, but in terms of speed, right? Remember that the orbit equation was there to give us the distance as a function of the true anomaly angle, but this one gives us the speed as function of the distance. So in other words, those two equations can ultimately be combined together to give us a relationship between the speed and the true anomaly, because this orbital position r is function of the true anomaly, and how to do it is through the orbit equation we saw previously. Okay, so that equation is a very important one. It's going to be used tremendously whenever we get into orbital maneuvers, because that will give us a way to calculate the amount of increase or decrease in orbital speed we need to change our current orbit to something else. That equation has a particular name, and it is known as the Vis-Viva equation. The Vis-Viva is Latin for live force. Don't ask me why that equation is called live force equation, because it's not about force, and I don't see why we would have a live or a dead force. Okay, this is in Star Wars here. So yeah, nevertheless, that equation is called the Vis-Viva equation. Okay, third most important equation in this course. The first one was the two-body equation of motion. Acceleration of a spacecraft is minus mu times r vector divided by the distance cube, which is r cubed. Second most important equation was the orbit equation, which was r equal P over 1 plus E cos theta. Or in other words, the relationship between the orbital distance r and theta, which is our true anomaly, which again is the angle between the eccentricity vector that points to the perigee and the current orbital position vector. And the third one is the Vis-Viva equation that gives us now a relationship between the speed and the orbital distance r, which can also be related to the true anomaly through the orbit equation. Okay? So, let's have a closer look at that equation for a little bit and discover a couple of interesting things. Well, actually, let's roll back to our previous expression for the speed for a moment. It's 2 times orbital energy plus mu over r, from which we have derived that Vis-Viva equation. Okay? So if we know that for a parabolic orbit, we had orbital energy exactly equal to 0 from our previous discussion on energy, it means that if you want to determine the speed at r equal infinity, you can use that relationship or that one, it doesn't matter, but let's use that one because we know how to relate it to orbital energy very easily. We're going to say that this is the speed infinity, meaning that this is whenever we have the limit of r towards infinity, whenever the orbital energy is equal to 0, so for a parabolic orbit, and we're going to get V infinity. Let me just write it higher up. That. Meaning that if orbital energy is 0, so that gives us 2 times 0 plus mu over infinity, because we're looking at the speed whenever we are very far away from the planet. So this is 0, and ultimately we end up with the velocity or the speed whenever r is equal to infinity for a parabolic orbit equal to 0. Okay? Exactly as we had determined from our previous discussion, or as I told you from our previous discussion, rather. Okay? So again, parabolic orbit, you barely have enough energy to escape, and you end up ultimately with no residual speed left. On a hyperbolic orbit, where we have orbital energy being positive, so in other words, sufficient energy to escape the gravitational field of the planet. Again, we're going to look at the speed whenever we had escaped the field. This is done by taking the limit of r towards infinity. Whenever e is a positive number, so we're going to say that this is V infinity equal to 2. Orbital energy, positive number, plus mu over r, square root of. So r is still infinity, so this term cancels out. And we're left with the speed at infinity equal to, as I told you earlier, a positive number. So we have enough energy to keep moving forward with a positive speed even after we had escaped from the gravitational attraction from M1. Okay? So those are just interesting facts about the orbital speed on those two trajectories as opposed to orbits. And also, through this section, we have just derived the third most important equation in this course, the Vis-Viva equation that relates orbital speed to orbital position r. Okay? Good, good. So I think that this is it for section 2.4. Now we're going to move on to 2.5, where the objective of 2.5 will be to derive expressions that will allow us to relate the true anomaly, or the angle between the eccentricity vector, which is fixed, so that's our fixed reference, and the position vector that keeps rotating around as the spacecraft rotates around M1. So to relate that angle to the time, because so far we didn't have the time explicitly appearing in our equations. So that's what we're going to do in 2.5. And to do it, we'll have to use Kepler's time equation. 2.5. Kepler's time equation. As I told you up front, we're going to first do the work for circular orbit, because this is kind of a trivial case to look at. And in fact, for circular orbit, there's no need to look at Kepler's time equation. Kepler's time equation will be derived throughout the process of relating true anomaly to time, but for the elliptical orbit case, which is quite more a long derivation to do, and that's why we're saving that one for the next lecture, okay? So today what we want to do first is look at 2.5.1, circular orbits, and again, how to relate true anomaly as a function of the time on orbit, okay? So if you remember from before, we had an expression for the specific orbital angular momentum h, which was equal to the distance square times theta dot. And actually, we didn't derive that equation together, because I believe I told you back then that that was one of the problem questions, so you'll have to derive that yourself, okay? Which means that the rate of change in true anomaly is simply equal to h over distance square on orbit. Okay? Now, let's open a quick parenthesis, and let's go back to our orbit equation, which was P over 1 plus E cos of the true anomaly, or alternatively, R equal to h squared over mu over 1 plus E cos theta. Now, because we're dealing in that subsection with circular orbits, it means that we know that we have the eccentricity exactly equal to 0. Okay? So in that case, we then have R equal to h squared over mu over 1 plus 0. So simply h squared over mu. Okay? Which means that we can further say that if we were to solve that equation for h, it would come down to h equal r times mu, square root of that. So I'm going to come back here and substitute my h for this expression and see what we end up with for theta dot. So theta dot would be square root of r, square root of mu, divided by r squared. Or in other words, that would be square root of mu over r cubed. So the rate of change in true anomaly is equal to the square root of mu, which is a constant, over r cubed, r being the distance between M1 and the spacecraft. interesting because we know that for a circular orbit, okay, so you'll have to pretend that this is a perfect circle centered at M1. Well, we know that that distance r at any point along a circular orbit is actually constant because this is a circle. Okay, so the distance between the center and the orbital path is not changing as it is for an elliptical orbit, such that r is constant and is also equal to the semi-major axis of this specific ellipse, which happens to be a circle. Okay, so we're going to say r equal to a, which is constant, and therefore we can say that this is square root of mu over a cubed. Huh. Have we seen that in the past? Yes, we saw that expression in the past. And in fact, we had called this n, the mean orbital motion, which was the mean rate at which the r vector sweeps throughout the orbit in terms of angular velocity, okay? So this is the speed at which theta evolves over one orbit. Now, this is a constant, and therefore the mean motion is also constant, as we've discussed in the past. So that makes sense, right? That for circular orbit, theta dot is a constant number in terms of radians per second. So in other words, the spacecraft does not accelerate or decelerate throughout the orbit. Okay? Or in other words, the position vector r, because yes, there is an acceleration by virtue of the two-body equation of motion, minus mu over r cubed times r vector. But what I mean is that the position vector, in terms of its angular motion, does not accelerate or decelerate as it does for an elliptical orbit. Because remember, about the apogee of an elliptical orbit, r decelerates, and then when r gets closer to the perigee, we accelerate again, decelerate, accelerate, okay? But here, theta dot is truly a constant for a circular orbit, and is exactly equal to n, the mean orbital motion, which is calculated as square root of mu over a cubed. Good. Now, we still don't see explicitly the time dependence in that expression. Well, that's not a big deal, because all we have to do is recall that theta dot is actually d theta over dt, right? This is the time derivative of the true anomaly, which is also equal to n, right? Theta dot equal to n. We have just established that, meaning that we can write that d theta is equal to n dt, which means that next what we can do is to integrate theta from some initial theta up to whatever value, and then integrate this side from the initial time to the current time, right? Initial time associated with the initial angle up to the current time associated with the current true anomaly. And that would just mean that on that side we get theta minus theta dot, or a change in true anomaly, equal to n, which is a constant, times current time minus initial time, t naught. Or, in a more compact form, I'm going to say that this side here can be rewritten as a difference in true anomaly angles, so delta theta equal to the mean orbital rate, or the mean orbital motion n in radians per second, times a difference in time, delta t. And this is how we can relate a change in true anomaly from, say, 0 to 45 degrees and a change of time. So if you're wondering how long would it take me to go from this orbital position at true anomaly equals 0 and the perigee up to, say, 100 degrees here. While if you are orbiting along a circular orbit, this is very simple because all you have to do is say, okay, 100 degrees equal to the mean orbital rate. In that case, we have to put it in degrees per second times what you're looking for, solve that equation, and then that would give you the time it takes to go from here to here. Okay? So that is the beauty of relating a true anomaly to time, because we can answer that question. How long does it take me to go from that initial angle to that final angle? Is it 10 seconds? Is it 10 minutes? Well, you just solve it to that very simple equation here. And the reason why that relationship is so straightforward and simple is because we were dealing in that subsection with circular orbits. So in the next lecture, we're going to have a look at elliptical orbits, for which the process is not as straightforward, and in fact, it has to be done in 2 steps. The first step will be to relate, this is just a heads up for the next lecture. So we'll first relate our true anomaly angle to a new variable denoted as capital E, which is the eccentric anomaly. And then as a second step, we'll have to relate the eccentric anomaly function of time. Okay? So we'll say, okay, in 45 seconds, this is how much eccentric anomaly the position vector covers. And then from 45-degree eccentric anomaly, how does that translate in terms of true anomaly? All right? So this is what we're going to do in the next lecture. But that's about it for today. Again, I hope you enjoyed. Hope you understood a little bit better elliptical orbits, parabolic orbits, and hyperbolic orbits in terms of their orbital energy, negative, 0, and positive, respectively. Hope you appreciated the fact that we've derived the third most important equation in this course, which is the Vis-Viva equation. That, again, relates the orbital speed to the orbital position. And finally, how can we relate true anomaly to time for the circular orbit? That was kind of a straightforward process, but you'll see next time that for the elliptical orbit, it is not as straightforward, or in other words, it is a lot more interesting. Okay? See you next time.